So hello, my name is Gonzalo Abad, and I'm going to do the presentation entitled Mathematical Model Equations and a Stationary Reference Frame of Current Controls for Grid-Connected Converters. All the information related to this presentation has been published in this book, in which the author is myself and Ander de Marcos, and it has been edited by Mondragon Unibertsitateko Zerbitzu Editoriala, this year 2019. So the contents of this presentation is divided into 6 different parts. First of all, I will do an introduction. Then I will show the control of currents in a stationary reference frame, alpha-beta control, also called. Then we will go for the control of currents in rotating reference frames, DQ control, with cancellation of coupling terms. After that, we will go for the control of currents in rotating reference frames, DQ control again, but in this case without cancellation of the coupling terms. We can have these both options. Finally, we will do a short comparison and analysis, and shortly, at the end of the presentation, I will do I will remark some future analysis. Okay, so let's go now with the introduction. So, grid-connected converters, power electronic converters, are used in many devices that we can find nowadays. Here I have made a compilation of some typical ones. First of all, wind turbines are characterized because they use power electronic converters, and these wind turbines could be onshore or offshore. In vessels or ship propulsion, also we can find power electronic converters, for instance, in order to create the internal grid for supplying the different loads and some other applications within the vessels. Then also, for instance, we can find power electronic converters in STATCOMs or active filters that nowadays are used in order to improve the grid quality. And finally, here you can find another example in which, for instance, the power electronic converters are also used, which is the photovoltaic generation. So normally, in a power electronic converter, which is connected to the grid, here we have the grid, the AC grid, that in this case we are going to focus on the 3-phase grid, which is the most typical one. Then we could have also a transformer. Not in all the previously mentioned applications we can find a transformer, but normally there is one. Then we have the filter, and this filter could have different topologies, but it is almost compulsory to have a filter within the transformer and the power electronic converter, where the semiconductors, IGBTs, diodes, and MOSFETs, and maybe others, could be placed. Here, the power electronic converter nowadays could have different topologies, like 2-level converters, 3-level converters, or even more level converters, and within them, different topologies. Then here, depending on the application, we could have battery packs or other converter, or even nothing, as for instance in reactive power compensators such as STATCOMs or active filters. And finally, here we normally, in almost all these applications, we have the current control, in which the objective is to, as the name says, to control the currents. And these current references normally are given as D component of currents and Q components of currents. And depending on the application, there could be a high-level control strategy, in which in this presentation here, in this high-level control strategy, we are not going to focus. we will focus only on the current control, in the lower control strategies. So depending on the current control that is employed, we normally do the control by using different reference frames. One reference frame could be the alpha beta, which is stationary, which is not moving. And here we could represent one space vector, x, that could be a current or a voltage within this power electronic converter, and its projections to this alpha beta reference frame could be these ones, alpha and beta. However, also we could have another reference frame which is moving at this speed, omega speed, which is the frequency in radians per second of the electrical grid. And the projections of this space vector could be also in this D and Q reference frames. So we will combine these two reference frames. And normally these references for the currents, the D, they are given in DQ reference frames, in rotating reference frames. Okay, so the simplified equivalent electric circuit in the alpha beta reference range is represented into this slide. Here we have the alpha and beta components of the voltage created by the power electronic converter. Here we have the equivalent circuit for the filter, that in this case we have simplified it a lot, and we are using only an inductive filter, but here often these inductive filters present a small resistance, parasitic resistance, and this is the one, this resistance. And finally here we have the alpha and beta components of the grid voltage. Here we have the alpha current going through the alpha circuit, and here we have the beta current going through the beta circuit. So the voltages of the power electronic converter, these two ones, are automatically generated by the current control that we are including or that we are using in this converter. Okay, so let's go now for the second part of this presentation, which is the control of currents in a stationary reference frame, in alpha beta, the alpha beta control. So the basic block diagram that we have for this alpha beta control is as represented here. Here we have the two components of current references in DQ. Then we have the reference frame transformation into alpha beta, and in order to do that we need the theta angle that is normally given by a PLL, and this PLL synchronizes this angle from the alpha and beta components of the grid voltage. In order to do simpler analysis in this presentation, we have considered, or better said, we have neglected the PLL. We have supposed that this theta angle is ideal, and we know it, and it's taken from this grid. Then once we have the alpha beta references for the current, they are compared with the actual or measured currents, alpha beta, the errors are calculated, and they are passed through the resonant regulators. Then we can provide these two feed-forward terms of the grid voltage, and from these loops, these two current loops, we finally create the alpha beta components for the voltage of the converter. These voltages are these two voltages of the converter in the alpha and beta electrical circuit, and they create the currents alpha beta that we want. Okay, so if we derive the time domain equations of this control, alpha beta control, we have these two equations in which this product is the convolution product, and then here also we have some time domain products. So we have two nature of products here. So this cosinus and sinus in these two equations are coming from this reference frame transformation. Then here we have the resonant controllers. And as you can see, or you can deduce, we have divided this equation through here. This is this term. And the measured current through here is this other term. And the same happens with the beta component. So now what we are going to do is try to solve this equation, these two equations in Laplace domain by using the Laplace transformation. But first of all, before doing that, I would like to remark that if you realize here we are generating the current reference in continuous, at least in the steady state, in a DQ reference frame, then we are transforming in sinusoidal current references. Why? Because basically these two circuits are working with sinusoidal currents, as in here. And finally, the references for the voltages of the converter, for the converter voltages, are also sinusoidal voltages. So this control operates partially and dominantly or mainly in sinusoidal operation at the steady state, while the references are in DC. So here is the equation given or employed for the resonant regulators that we employ at both loops. Here it is the equations in S domain by applying the Laplace transformation, being Kp and Ka, two gains that must be tuned, and being omega, as we said before, the radians per second of the frequency of the grid. So if we are in a grid of 50 Hz, that will be more or less 314.16 radians per second. And here we will consider step inputs for both components of current references in D, E, and Q. So the equations in Laplace domain, in S domain, are these ones. So after several mathematical developments, which are not so simple, they are quite large, so we can obtain the result of these two previous time domain equations in S domain equations. And here we see that the alpha component of the voltage created by the converter, after applying these loops, is multiplied by the equation of the resonant controller to the alpha components of the current. Then there is another term that multiplies the D reference of the current. Then also there is another component that multiplies, another term, sorry, that multiplies the Q component of the current reference. And here we have the coupling terms. And for the beta component of the converter voltage, we have something very similar. These two equations are very symmetrical. Here we have same term, and this term could be equal to this one, is equal to this one, while this term is equal to this one. So now, if we analyze the time domain equations of the power circuit, the grid, filter, and the power electronic converter, we have these two equations. in time domain, while if we apply the Laplace transform to these two equations, we obtain these two other equations depending not on the time but on the S operator, such in here. So if we combine these power circuit equations, with the previously derived control equations provided by the current control, these two loops that have this structure, the equations have been derived in the previous slides. You know that we can equalize this voltage to this voltage and this voltage to this voltage. So if we combine all and we do several developments and we just derive the currents alpha beta in function of the references D and Q, we obtain this. We see how the alpha component of the current depends on the current reference multiplied by this term and being this denominator equal to this equation. So it is a third order equation. That means that we have three poles. Then we have the Q component of the current reference that is multiplied by a very similar term to this other one. And again, we have here this denominator, which is this one. And for the beta component of the current, we have something which is very symmetrical, because here we can see that these two terms are equal. There is only one minus of difference between them. And here, these other two terms are equal. So we can say that the alpha and beta components of the current for this alpha beta control depend on the two inputs, referent currents in dq, and they are multiplied by these two terms. This will be this term, and this other will be this term. This term will be this one, and this term will be this one. So this is another different way of representing the same. And these are the closed loop expressions that represent the output currents in function of the references, which are the input currents. So if we now substitute at the current references the step inputs that we are analyzing in this case, and developing a little bit these two expressions, we obtain this. And here you can see that these are the amplitude of the current references for dq, for d and q. And then here we have a third order system of three zeros. Here we have two zeros. Here the symmetry between these two. And for the denominator, we can see that we still have the A equation, which are three poles, and then we have another two poles at omega in the imaginary axis for both. If we solve these expressions, these Laplace domain expressions, and we derive or we obtain the time domain expressions from them, we have, for instance, for alpha current, but something very similar would be obtained for beta current, but for alpha current, we have one expression multiplying the D amplitude for the current reference for D, and we obtain something very similar multiplied by for the Q current. This is an exponential term. This is a complex conjugate term. This is coming for a pole which is complex conjugate. This is a real pole. And here we have the same. And here we have the same. And these two terms are stationary terms. They do not extinguish as these two ones. Since they are multiplied by the exponential, they will be zero at zero state, at a steady state. So they will disappear, and these terms will be the steady state terms. One cosinus and another cosinus with a p over 2 degrees of phase shift. If we represent all of these in Simulink blocks in order to validate what we have obtained, the expressions that we have obtained, because we need to make sure that these derived expressions are okay, are good or not good. So we developed, for instance, the Simulink expressions, as in here, the Simulink blocks, control block diagram. This is the transformation from dq to alpha beta. This is the resonant regulator for alpha component. And this is the other resonant regulator. This is the idealized theta angle. And this will be the power electronic circuit. This is the two filter equivalent expressions in Laplace domain. And this will be the two voltages for the grid. So if we give numbers for the Kp and Kai gains for the regulators, and also for the filter, and also for the grid frequency in radians per second, we give these numbers to this block diagram. And for instance, using the residue function from MATLAB library, we can obtain all the gains for the time domain expressions for an step inputs of the previously derived transfer functions in Laplace domain. So the Laplace domains that we have derived expressions, we obtain then the time domain expressions, and we can obtain these gains by using one function, for instance, from MATLAB. And these numbers are the ones provided by this function. As I said before, this is the transient response because this is made zero at the steady state. In other places or in other terminology, we can call it natural response to these terms. And this is the steady state response, the steady state remaining terms that also could be called the forced response. So if we plot both the voltages of the converter, the currents in alpha beta, and the natural response, for instance, only for alpha component of the current, and we superpose, we compare both the one given by the Simulink blocks and the one given by these equations, and we have substitute these numbers, we see that we have an exact match. They are exactly the same. So we can say that they are properly validated. Okay, if we continue with the analysis, we come back to the previous transfer function expressions in Laplace domain, which were these ones, and we now, by using again the MATLAB library, we can obtain the pole zero map of both transfer functions for alpha current and beta current. This, please remember that these were the closed loop expressions. So here we realize by only paying attention to the poles that we have in both D and Q currents one pair of imaginary poles at omega and minus omega, which is coming from these terms at the denominator. Then we also have another three poles, one real pole and one complex conjugate poles that are coming from the roots of these equations, which are present in the four terms. And this happens the same in both currents. So these three poles are the poles that are extinguished at the steady state. So they are the transient poles, the ones creating the transient poles, or the ones that are multiplied by the exponential terms, while these two poles are the responsible for the steady state. So these two poles are the steady state. Sorry, these two terms are coming from these two poles, and these natural or transient response are coming from these three poles. These two poles is this real pole, and these two complex conjugate poles are these terms. And these are the time domain expressions, please remember, for step inputs. Okay, so coming back to the previous slide, in which we have represented the control block diagram of the control that we are analyzing, the alpha beta control. Here we have the electrical circuits in alpha beta, and these voltages are provided by each loop of this control strategy. And remember that we can obtain the time domain expressions or equations of this control. And these are the two equations. So now we are going to see what happens if at the input references for the currents in DQ we replace or we demand sine and cosine inputs. So please keep in mind the time domain equations for both D and Q components of the currents are these ones, and please remind that the Laplace transform of these sinusoidal and cosinusoidal equations are provided by these two equations, S domain. So if we solve these time domain equations and we derive the Laplace domain equations with the S equations, after substituting these two inputs, the obtained expressions for alpha and beta voltage in function of the current references, which are sinus and cosinus, are rather more complicated than the previous ones with step inputs. Obviously, it happens like that. So here in both voltages, we have the resonant controller multiplying to all these terms. Here we have the alpha and beta currents, actual currents or measured currents. And then here for D current reference and for Q current reference, we have some other two terms which are more larger or more complex than the previous ones. Here for alpha voltage and here for beta voltage, these two terms. Again, there is a short symmetry between both. And finally, here we have the feed-forward terms of the grid voltage. So if we mix or if we connect these equations, which are the equations describing this alpha-beta control in Laplace domain, if we combine them, I said, with the Laplace equations of the power electronic circuit, or the electrical circuit, these two equations that we have derived previously. So if we equalize these two equations, we obtain another two expressions, which are the closed loop expressions that represent the alpha current and the beta current, the actual currents, sorry, in function of the D and Q current references for both. Compared with the step inputs, we obtain a little bit more complicated expressions because the inputs are a little bit more complicated, so therefore the expressions are larger. They have more terms. Here again, just keep in mind or just see that in both currents, alpha and beta, we have at the denominator again the same as before. These third order equations that depend on the filter and the grid frequency. And obviously, again, it also depends on the Kp and Ki, the gains of the resonant regulator. So once we have the transfer function expressions, and if we substitute the sinusoidal and cosinusoidal inputs at these two expressions, and we rearrange the terms, we obtain these two expressions, which are the expressions that can give us these alpha and beta currents after substituting these two inputs, obviously. So rearranging the terms and giving a little bit order to both currents, alpha currents is here and beta currents is here. So if we focus, for instance, only on alpha current, we realize that we have one term multiplied by this element and we have another term multiplied by this other element. This is a sinusoidal of omega 1 plus omega frequency, and this is another sinusoidal of this frequency, omega 1 minus omega. And these two sinusoidals are multiplied by one term that depends on the amplitude of the current inputs, this one and this one, and then again we have the equation with the three poles and the second order zeros that depend on basically the gains of the regulator. And something very, very similar we have in beta current. However, here, instead of having a sinusoidal, we have a cosinusoidal. And here again, we have another cosinusoidal term. In general, we can see that in the typical classic books, this is by using these two expressions are how the body diagrams are originally defined or obtained. So the output current alpha, if we focus on this expression at steady state, is composed by the addition of two sinusoidal frequencies, one given by this term and the other one given by this term. And these terms, let's say that the time domain equivalent terms of these two expressions will be extinguished, will be at the steady state. So the amplitudes of the body can be calculated by substituting in here the frequency of the sinusoidal, omega 1 plus omega, and the other term, the other amplitude corresponding to this sinusoidal will be or can be obtained by substituting this omega 1 minus omega at this expression. So, rearranging the terms and substituting the denominator expression, we have this third order system, 3 poles in both and 2 zeros. So if we do zero the Q component of the current in order to simplify the analysis, and we only consider the sinusoidal input at the D component of the current, and for instance we give some numbers, 1 ampere of amplitude, and the frequency that we choose for omega 1 is 250 Hz. If we substitute and we calculate the body by using, for instance, the body function from MATLAB, we obtain this body diagram in which at the first frequency, omega 1 minus omega, we obtain these radians per second, which are basically 200 Hz, and this basically this frequency that can be obtained from this spectra that it's taken from the time domain. And this amplitude, which is 1.17 or even more, 18 more or less, corresponds to this magnitude in decibels. And in time domain, the other frequency, this one, 300 Hz, this was 200 Hz, this was, and this is 300 Hz, corresponds properly as well with the time domain, this time domain sinusoidal current at the output corresponds with the one given by the volt diagram. Sorry, these are the values, 1.87 and 1.127 amperes for 300. That corresponds with these decibels in the frequency response. So what I want to say is that there is a total correspondence between the time domain and frequency domain. And this is given by these expressions derived from the ones that we are obtaining in this analysis. By obtaining now the time domain expression, we can obtain this rather more complicated equation. We have one term that depends on the D amplitude of the sinusoidal, and we have another term that depends on the Q amplitude of the cosinusoidal in this case that we are analyzing. So here we have, as before, one real pole that gives us only an exponential term. These two terms, sorry, let me have a look. Yes, these two terms are provided by the complex conjugate poles of this, which are here. And these two terms are the sinusoidal and cosinusoidal terms that remain at a steady state for both, at one frequency and the other frequency, for D input currents and for Q input current. So by using one function, residue function from MATLAB Simulink, we can obtain the numerical values for these gains. Sorry. And we can say that here, I'm not going to show it, but in the book it is provided, that again, if we compare this expression, these analytically obtained expressions with the one given by, for instance, the blocks provided in Simulink, there is an exact match, so we can say that they can be validated, or they are validated, they are true, they are good. So continuing with the analysis, let's come back again to the closed loop expressions that we have obtained before. These are the transfer functions, and these transfer functions are only valid when we have D at D and Q current references, sinusoidal and cosinusoidal current references. So now, if we obtain from these two transfer functions the pole zero map, we can have this, for instance, by using again MATLAB toolboxes. And if we focus only in the alpha current, which is this one, we realize again that we have two imaginary poles at omega 1 minus omega and omega 1 plus omega, which are given by these two terms. Then we have a zero at omega 1 here and here, again complex. And then here we have the three poles corresponding to these two, to this expression, which is these third order expressions, one real pole and two complex conjugate poles. And this is the same for D and Q. So if we compare the pole zero map with sinusoidal and cosinusoidal inputs and the one that we have obtained before with the step inputs, we see that these three poles are the same, the scale are different, but the poles themselves are the same. Yes. Check the numbers. And what's changing, so this means that the transient response is equivalent or is given by the same dynamics because we have the same poles. And what changed is the steady state, that for step inputs we have only one frequency, omega frequency, while when we have sinusoidal and cosinusoidal inputs, we have at the output two frequencies, omega 1 plus omega and omega 1 minus omega.